AI is not a software story anymore. It's an industrial system. Most people focus on ChatGPT, apps, and models, but they are only the top layer. Underneath, there's an entire infrastructure stack, from chips, networks, data centers, all the way down to electricity. In this video, I'll break down the 8-layer AI infrastructure model, and more importantly, show you where the real bottlenecks are. Because in this game, the winners are not who build the best AI, but who control the system behind it. Silicon brain, compute core. The first layer of the AI infrastructure stack is the silicon brain, the compute core that powers all artificial intelligence systems. This includes GPUs, CPUs, and the advanced semiconductor manufacturing processes required to produce them. Companies operating in this layer define the upper bound of computational capability, determining how fast models can be trained and how complex they can become. Without continuous improvements in chip architecture and fabrication technology, the entire AI ecosystem would stagnate. However, from a strategic and investment perspective, this layer is no longer the primary source of asymmetric opportunity. The market has already recognized the importance of compute, leading to significant capital inflows and elevated valuations. In financial terms, this is a crowded trade where expectations are high and future returns may be constrained by already optimized pricing. While innovation continues, the marginal upside is increasingly limited compared to earlier phases of the AI cycle. For operators and strategists, the key insight is that compute alone does not create value unless it can be efficiently deployed within a broader system. Raw processing power must be integrated with networking, storage, and energy infrastructure to become economically meaningful. As a result, while this layer remains foundational, it is no longer the primary bottleneck. Compute networking, the real bottleneck. The second layer represents the networking infrastructure that connects compute resources into scalable systems. In modern AI architectures, individual GPUs are no longer sufficient. Performance depends on how effectively thousands of units can communicate and synchronize. This is where high-speed interconnects, optical communication, and data transfer protocols become critical. The industry is currently undergoing a structural shift. The bottleneck in AI performance is moving from compute generation to data movement. Even the most powerful GPUs become inefficient if they are underutilized due to latency or bandwidth constraints. In practical terms, this means that a poorly optimized network can turn a high-cost data center into an underperforming asset. From a systems perspective, networking is the circulatory system of AI. It ensures that data flows seamlessly between compute nodes, enabling parallel processing at scale. As model sizes increase and distributed training becomes standard, the importance of this layer grows exponentially. From an investment standpoint, this layer offers a more favorable asymmetry. It is less visible to the general market but increasingly critical to performance. As a result, it represents a high-potential segment where demand is structurally driven by the scaling requirements of AI workloads. Physical infrastructure, data center backbone. The third layer consists of the physical infrastructure that houses and supports AI systems. This includes data center design, cooling systems, power distribution units, and rack-level engineering. While often overlooked in software-centric discussions, this layer determines whether AI can operate reliably at scale. AI workloads generate extreme heat due to the intensity of computation. Managing this thermal output is not a trivial engineering problem. It directly affects system stability, operational costs, and hardware lifespan. Inefficient cooling can lead to performance throttling or even system failure, making it a critical constraint in real-world deployments. Additionally, power distribution within data centers must be carefully engineered to handle high-density loads. As compute clusters become more concentrated, traditional infrastructure models are no longer sufficient. This forces a redesign of data center architecture, prioritizing efficiency and scalability. From a strategic standpoint, this layer represents the transition from digital abstraction to physical reality. It highlights the fact that AI is not purely a software phenomenon, but a deeply industrial system. While the growth potential is stable rather than explosive, this layer is essential for enabling all higher-level applications. Digital memory, storage layer. The fourth layer focuses on storage systems, which function as the long-term memory of AI. While compute handles real-time processing, storage preserves data, models, and inference histories, enabling continuity and learning over time. Without robust storage infrastructure, AI systems would be limited to short-term, stateless operations. Modern AI applications require massive datasets for training and continuous updates. This creates demand for high-capacity, high-speed storage solutions that can support both throughput and latency requirements. Furthermore, as models become more complex, the need for efficient data retrieval becomes increasingly critical. Despite its importance, this layer often receives less attention in mainstream AI narratives. The focus tends to be on model performance rather than data management. However, from a systems perspective, storage is indispensable. It ensures that knowledge is retained, reused, and scaled across applications. From an investment perspective, this layer may appear undervalued relative to its strategic importance. However, it typically lacks strong narrative catalysts, making it a slower-moving segment. The opportunity lies in recognizing its foundational role before it becomes a visible constraint. Compute operators, AI infrastructure providers. The fifth layer introduces a shift in business models, from selling hardware to monetizing infrastructure. Compute operators aggregate GPU resources into large-scale clusters and offer them as services. This transforms compute into a rentable asset, similar to how cloud computing revolutionized traditional IT infrastructure. In this model, the value is not in owning chips, but in orchestrating them efficiently. Operators manage capacity, optimize utilization, and provide scalable access to AI resources. This creates a recurring revenue model that is structurally different from hardware sales. This layer can be understood as the landlord of the AI economy. Just as real estate owners generate income by leasing space, compute operators generate income by leasing processing power. The analogy extends further. Location, efficiency, and operational expertise all influence profitability. From an investment standpoint, this layer offers high growth potential, but also carries significant risk. It is still in an early stage of development, and its success depends on demand stability, capital efficiency, and technological differentiation. Energy storage, stability layer. The sixth layer addresses energy storage, which plays a critical role in stabilizing power supply for AI systems. Data centers experience fluctuating energy demand, especially during peak computational workloads. Without buffering mechanisms, these fluctuations constrain the grid and disrupt operations. Energy storage systems, such as batteries, act as buffers that absorb excess energy and release it when needed. This ensures a consistent power supply, reducing the risk of downtime and improving overall system reliability. In the context of AI, where uptime is crucial, this function becomes indispensable. This layer highlights a key reality. AI is not only a computational challenge, but also an energy management problem. As demand for AI services grows, so does the need for stable and efficient energy infrastructure. From a strategic perspective, energy storage represents a long-term growth opportunity. It is closely tied to broader trends in renewable energy and grid modernization. While it may not generate immediate returns, its importance will increase as AI adoption scales. Power generation, the true limit. The seventh layer is the foundation of the entire AI system, power generation. All computational processes ultimately depend on electricity. Without sufficient energy supply, no amount of technological advancement can sustain AI operations. As data centers expand, their energy consumption reaches levels comparable to small cities. This creates a direct link between AI growth and national energy infrastructure. Traditional energy sources, such as natural gas, coexist with emerging solutions, like nuclear and renewable energy. The critical insight is that energy availability sets the upper limit for AI scalability. While software and hardware can be optimized, they cannot operate without power. This makes energy the ultimate constraint in the AI value chain. From an investment perspective, this layer represents a foundational asset class. It may not exhibit rapid growth, but it provides long-term stability and strategic importance. In many ways, it is the most underappreciated component of the AI revolution. Application layer, distribution and monetization. The final layer is where AI interacts with users, the application and distribution layer. This includes cloud platforms, enterprise software, and consumer-facing AI products. It is the most visible part of the ecosystem and often captures the majority of public attention. Applications translate underlying infrastructure into usable services. They define user experience, control access points, and determine pricing strategies. As a result, they play a central role in monetization. However, this layer is also the most competitive. Barriers to entry are lower compared to infrastructure layers, leading to rapid innovation, but also intense competition. Companies must continuously differentiate themselves to maintain market position. From a strategic standpoint, this layer depends entirely on the stability and efficiency of the underlying stack. While it captures value, it does not control the fundamental constraints. Therefore, its long-term advantage lies in integration rather than isolation.